Okay. Yeah, before we go into the organizational stuff, there is already a question in chat. Will I record the lectures? The answer is no. I will not put recordings online. I do not record this lecture, so you have to show up every week at the same time because this is like a live lecture. Regarding tech stuff, well, I mean, you're in the call, and I have to admit the rest of the people. You are now in the call, and this will be our way how we do the lecture every week. So we meet at 9:45 sharp every Tuesday, 9:45 in Central Europe time. Be aware that Central Europe, or especially Germany, has 2 time zones, which is like suboptimal, so to say. But we have 2 time zones. We have a summertime and we have a winter time. And right now, I guess we are still in summertime, but we will switch to winter time pretty soon. I don't know the exact date. I guess it's end of the month, end of the October. Let me just Germany start of winter time. Let me Google that for you. Yeah, it's end of October. Then we change time zone, and then we have a shift in starting the lecture by 1 hour. So be aware that we have 2 time zones in Germany. Okay. Next. Yes, the stream is in full HD. I recommend everyone to watch the stream on a reasonably sized display. So at least full HD, such that you can read everything that will be on the slide. I mean, I know people are joining from phones. Tablet is like borderline. If you have a good tablet with a reasonably large screen, then this is fine, but do not follow the lectures in bed on your smartphone, because you should follow the lecture, you should work with me, you should ask questions in Zoom. If you can ask questions via microphone, yes, and this should be the default way that we interact with each other, because it's, I mean, there's a barrier between us, me talking the most time and you talking a little bit less than me, but still, like, lectures live from interactions, and interactions are harder if we do it remote than compared to we meeting in a lecture hall, and you can just like raise your hand and ask your question. You can do both. So you can write text messages. I will take a look at chat from time to time, but you know, if I'm telling you a story and I'm full in my process of telling you something, I might miss the chat message, but usually every 10-20 minutes I will take a look at chat and try to answer questions there. You can also do the emotes in Zoom. So I have Zoom open on a second monitor, so I should see if you do the raise hand reaction. I mean, we can try this out right now. So please give me a reaction, not a hand raising reaction, but give me a reaction, like a green check mark yes. And I will do this regularly because I can see how many yeses are there in the chat. So I can calculate the ratio of how many participants are in the call and how many reacts do I get. And this is the way how I see who is sleeping and who is not sleeping. And as of right now, I got 14, 15 reacts. I mean, some toggle on and off. Let's say 20, 30. So half of the people is sleeping apparently, and some are not. And If you have a question, you can do the raise hand reaction, and then I will stop and try to answer your question. Then you can speak up via microphone. So, admitting people. This is annoying because people like drop in, hop off of the call, and I have to admit all the people joining in. As I said in this call, hopefully Zoom will reconsider, or Zoom will apply the reconfiguration of the call for the next time. Also, recommendation is to have a nice hot beverage. Make yourself comfortable as at home, not as comfortable as being in bed and watching via smartphone. You should sit on a chair to like do something as well, and carefully listen to the lecture. Okay. How can you contact me? Well, I assume, because this is the first semester for most of you, I assume that you are, or the majority of you, currently not in Germany. So we do everything remote. I do not have any dedicated office hours. If you feel the urge to talk to me, you can do this by dropping me an email. My email address is firstname.lastname@thdec.de. Be aware that I have a German umlaut, like Wölfel, right? The second character in my last name is an umlaut. And umlauts are mapped to OE in email addresses because, you know, umlauts and email addresses do not fit together very well. So my email is andreas.wölfel with OE encoding of the umlaut at th-dec.de. And then we set up a remote call, and then I tend to your matters, hopefully. If you want to talk to me in my office, I mean, maybe it's relevant for some of you. My office is not directly at the campus. It's next to the campus. It's the DEX building where the entrance is in Veilchengasse 15 to 19. So there is a small sign above the entrance door. This is not the main entrance. And in order to find the entrance, I have put an OpenStreetMap link here on the slide. This link is clickable, so you can download the slides, click on the link, and then you see where the entrance is. Also, the elevator, so my office is at the second floor. You see this at the office like number/name. It's 216, meaning floor is 2, and it's the 16th office in the floor. But if you take the elevator, you need to press the third floor. So I don't know how these people count in construction, but this is actually the second floor. But in the elevator, in order to get to the second floor, you need to press the number 3. I cannot say why this is the case. Okay, so this is how you find me, and this is how you contact me. This lecture, as every lecture at the Deckendorf Institute of Technology, is supported by an iLearn course. So iLearn is the platform where we distribute all materials, do announcements, publish things like slides or practice exercises and such. And if I switch over to my browser here, this is the course for operating systems and networks. It is absolutely mandatory that you are in this course. If you do not have access to iLearn in the first place, you need to contact the Center of Studies as soon as possible in order to get access to the iLearn platform. If you do not have access to the course operating systems and networks, this is the correct one. So every term and every year we have a separate course. So this is the one for the winter term 23-24. This is the correct one. If you do not have access to this course, but you have general access to iLearn, you can drop me an email and I can add you to the course. Again, it's absolutely mandatory that you are in the course, because you see we have the table of contents here. There's the contact information, but more importantly are, for example, the lecture slides. So all slides that you see here are published over iLearn. And also we have practice exercises that we do in class. Some we do in class, some I will assign as homework. But for example, we have an exercise here, computer architecture. There are small task assignments for you to work on. And this is all published via iLearn. So please make sure that you have access. Admitting people. Okay, iLearn. Next is table of contents. R. Unfortunate. Table of contents, as this is operating system and networks, we have two parts, and these two parts are divided evenly. So we have a part operating system with 7 units. Unfortunately, the class last time did not take place because of public holidays, so we start 1 week late. But still, it should work out. The winter term has 15 weeks in total, and for the operating system parts, I planned 7 units, so 7 weeks. Today, I will give you an introduction to operating systems. And from next week, we are starting with the Linux operating system. So a one-on-one how to use Linux, and we have a focus on the command line, because this is the most important tool for you as artificial intelligence students to know your way around the Linux operating system, especially knowing your way around with the command line utilities that are there. Then we talk about memory management. So I have flipped memory management and file systems. So we talk about memory management right after beginning with Linux. Then we talk about file systems, and then we talk about processes and threads. So this will be the operating systems part, the networks part, also 7 units. The introduction is not as comprehensive as for operating systems. You will see, the whole 2 blocks of lectures will be the introduction, because there's a lot to talk about operating systems to begin with. The introduction in computer networks will be a little shorter. Then we talk about network structures, like what devices are important to put together a network. What is a switch? What is a router? What is a repeater? Also, how can we put these devices together in a logical or physical arrangement, meaning that, the technical term for that is topologies, which will be a bigger part. Then we talk about data transfer and performance, meaning what are the basics? How does information travel from one host to another? And how can we assess how performant the network are? What are the key performance indicators there? Then I guess the most boring lecture over the course will be reference models, but we need to talk about these reference models, like the ISO-OSI model, the TCP/IP model, and such. The biggest part will be network protocols, where we talk about the actual protocol. How does Ethernet work? How does IP work? How does TCP work? How does DNS work, which is also protocol networking? And last but not least, at the end of the semester, hopefully you have picked up some knowledge in programming 1, such that we can take a look at how we do network programming. So how can 2 programs on 2 different hosts communicate over the network? And the technical term for that is socket programming. So this will be the contents through the whole semester. Okay, next, admitting people again. Oh, this admitting is annoying. A word or two about the workload, because this is, I state the workload pretty, explicitly, but this is the way how we as university docents and professors assess or plan with your time, and this is how we set the expectation, what is expected of you. So this course, operating system and networks, has 5 ETCS points. 1 ETCS point roughly translates to 25 to 30 hours workload. So 5 ETCS points are roughly 150 hours of workload in the semester. As we have 15 weeks in the winter semester, this means that you have a weekly workload of 10 hours on average every week. So this is what is expected from you, to put in 10 hours of effort into this module, operating system and networks. From this 10 hours, we have classes. We have what we call 4 Semesterwochenstunden. The closest English translation would be workload measurement. But if you encounter this abbreviation SWS, this means Semesterwochenstunden, meaning 4 like school hours, which are 45 minutes per week classes. So we have 180 minutes classes per week, 9:45 to 1 p.m. every Tuesday. And we split this up in 90 minutes of lectures per week and 90 minutes of lab sessions per week. But this lab sessions, meaning these are practice exercises. So I give you a task assignment, you work on the task assignment, and after you have done the task assignment, we will talk about it. I will not like separate this in a sense that we do 90 minutes lectures and then we do 90 minutes exercises. We will mix this in. So we have depending on the topic, like 15 minutes, 20 minutes of me telling you some things, and then we do a small practice exercise. And in this like mixing in practice exercises, we will spend the whole 180 minutes. But in terms of workload, meaning we have 3 hours, 180 minutes of classes per week, which leaves 7 hours per week for preparing for class, reciting, further readings, exercises, lab problems, preparing for the exam and such. So keep this in mind. I know that people work differently, and people tend to study more closer to the exam date. But my strong recommendation is please work every week for every module that you have, not only operating systems and networks, but try to distribute the workload throughout the semester, because otherwise you will have crunch time before the exam. And also, if you keep track with the subjects that we discuss in the lecture, you will gradually build up knowledge, and you are able to do the lab problems, the exercises, and this is easier for you over the whole course to distribute the workload over the whole course. And at the end of the semester, everyone, including me, wants you to have good/very good grades. Okay, having said that, yeah, lab assignments, these are practice exercises solved in the course of the lecture. We mix these in. These are more practical tasks around current subject matters. As practical it can get remote, and in the more theoretical contents of operating systems and networks. Operating system and networks is a little bit different from modules such as programming, because in programming you can do practical tasks all the time. You can program all day. In operating system and networks, we will also have practical tasks, like you calculate something, or you do something like research something or think about something, but it's more on the theoretical side than on the practical side compared to other modules that we teach in the first semester. They are published on iLearn, and a word on the difficulty level. Some of the tasks are easy, right? But some are slightly above exam level. So on average, the difficulty level of the practical tasks is slightly above exam level, such that you can do the following. You can solve all the exercises, all the tasks, and if you are able to successfully complete these tasks, then you are ready for the exam without any like aids such as ChatGPT or other AI assistants. If you use these AI assistants, well, you can do this, but you need to live with the consequences. So my take on ChatGPT is the following. I use it on a day-to-day basis, right? So this is, you need to think of this as a tool that makes you efficient, right? So use these AI assistants to like clarify things, to help you in understanding, to help you in the learning process, to be more efficient. Do not rely on AI assistants too much. So you still need to grasp all the subject matters in the lecture. And at the end of the semester, this is new compared to previous semesters. You need to take the exam in presence in Deggendorf. I mean, people surely have talked about this before. So in the last year, you could, or it was possible for you to do an online exam, but AI assistants are too present in this kind of online exams. I personally had to grade a lot of exams with a not passing grade because of proof of AI assistants. So this is not possible anymore. Please make sure that you do not rely too much on ChatGPT. So a question, when we will have the exams? I don't know. The board of examiners. So there's a couple of professors which are the board of examiners, and together with the study program assistants, they will determine the exam date. I don't know yet. I guess it is in the making, and you will get notified either from the Center of Studies or the study program assistants when the exams will take place. The exam is 90 minutes in presence, where 45 minutes are assigned to operating systems, 45 minutes are assigned to networks. I will do this 50-50, so these are exact 45 points for operating systems and exactly 45 points for networks. 1 point equals 1 minute. So if you encounter a question in the exam which has five points, then the time or the question is designed that you can do, or you can write down the answer in 5 minutes. So 1 minute is 1 point. The question design is a mix of calculations, knowledge, and transfer questions in the style of exercises. But a word of warning, the exercises that we do throughout the course will have calculations and will have transfer questions, sure, but they rarely have knowledge questions, because typically the answer in knowledge questions is somewhere in the material that we provide to you. So it's on a slide, for example. And having you like watching me explaining the contents of the slides and then we discussing and having like a knowledge question afterwards does not make sense, because you just take a look into the slide and copy paste this. In the exam, this is a different kind of situation. In the exam, we will examine if you also have the knowledge to pass this module. So there will be knowledge questions in the exam, and there will be practical questions such as calculations or transfer questions. I will publish a mock exam such that you have a look and feel how my exams look like and what my style of question will be. Typically 2 weeks before exam date, which is not fixated yet. You will see that my slide deck is more on the verbose side. So I have much information on the slide, such that you have a comprehensive material that you can study. And for you, I will grant an exam aid. Because my slides are a little bit more on the comprehensive and verbose side, I will allow a 2-page double-sided self-produced handwritten script in A4 format as exam aid. So when you come to the exam and you enter the exam room, you're allowed to use this 4-page script during the semester. So it needs to be 2 pages, double-sided, which equals like 4 pages handwritten. It needs to be self-produced, meaning that you need to produce this. So you cannot use a copy of a script from a colleague, and it needs to be handwritten in your handwriting. I will allow digital handwritten scripts. So if you own like an iPad or another tablet, you can produce this script using your iPad. You can print this out and you can bring it to the exam. Also, you can write as small as possible. So with like a digital stylus and an iPad, I guess it would be possible to put all the information of the slides on that script, but this is what I will allow. And then you can bring a non-programmable, non-graphic capable pocket calculator. You could do all the calculations in your head, but exam situation is like a stressful situation for students. So recommendation is to bring the calculator. There's a question. Rao, please go ahead.
Okay, sir. I have a question regarding the attendance. Is there attendance limit in the school?
No, no. You can join the call. You can drop off the call as you like.
I understand. One more question is about the quiz or test in the classroom. Is there such quizzes and exams or midterms in the classroom that will be added in the final grade?
No. So what I guess you're referring to like this task assignments.
Yeah.
For example, we have history of operating system, which is a quiz. This is just for you to for practice exercising. This will not count into the exam.
I understand. But we can ask questions regarding this, right?
Sure. I mean, we do this like throughout the introduction to operating systems. We are not there yet, but you will see in the course of today how this works. So we will have some discussions regarding history of operating systems, for example. And after I told you something about the history of operating system to practice this, then you do the quiz. And you have dedicated time in class in order to do the quiz.
I understand. So there will be just one exam in the final exam. There is nothing else.
No.
I understand. Thank you.
More questions in chat? Do you have answer sheets on these questions? The answer is no. You need to like attend to the lectures. We will discuss it, and you need to take notes regarding the solutions for the tasks. Except for quizzes. I guess quizzes tell you if the answer is right or wrong, so you can derive the solution from there. Then we have answer sheets. No. What possibly a script can contain? Everything that you like. So you can draw pictures on it. You can add like things from the slide to it. Everything is allowed there. So in this course, we do not have a midterm. That is correct. No midterm, one final exam at the end of the term. Rao, your questions are answered, right?
No, I have one more question.
Okay, go ahead.
You mentioned about one. There will be one exam, mock exam before the exam. So in that exam, there will be no answers, as you just mentioned. It will be just questions. There will be just questions. Will the answer similar to the real exam?
No.
No, I don't mean like exactly similar, but will they be similar in terms of pattern or something?
In terms
so,
of
for example, if someone is
style, yes.
If someone is able to do that mock exam by himself, it means that he is able to do the real exam as well, right?
That's a trick question. I cannot say, because these will be entirely different questions, right? So,
I mean, in terms of difficulty level.
yeah, difficulty level is the same.
Okay.
So all the course weightage depends 100% on the final exam. Correct. Okay. Any more questions on the exam? Okay, then let's talk about literature. In the operating system parts, in both parts, in the operating system parts and the networks parts, we have a book from Andrew Tannenbaum. The operating systems book is Modern Operating Systems from 2014. This is the main source for this this course, and it's, in my opinion, the best book on operating system and networks. It's a good book for classes, because at the end of every chapter there is a section where you can or a section with exercises in addition to the exercises that we do in the course. So if you want to take at secondary literature, I encourage everyone to do so in order to skill up the knowledge. And the main book that we use for the operating systems part is the Tannenbaum book. If you do not find an information, or if you want another book where you want to take a look at, I will recommend the Silberschatz book, Operating System Concepts, which is also a good teaching book on operating systems. And the third one that is mentioned here is only for the lecture on the Linux operating system. So Mastering Linux System Administration is the accompanying book for the next bigger section that we will have in the course. And all the other sections, such as file systems or memory management or processes and threads, these are covered in the Tannenbaum and Silberschatz book. For the networks part, there's also a Tannenbaum book. It's called not Modern Operating Systems. This one is called Computer Networks, which is right now in the 6th edition, 2021, the book to go for all network-related part. I have also the Network Warrior on the list. I mean, when we talk about subnetting, there is some useful information in the Network Warrior book as well. But Network Warrior is more a practical-oriented book, mainly focused at Cisco certifications, but still it's a very, very good practitioner's book. So I have put this on the list, but main book for the course and for all the materials that we discuss in the part of the lecture is from Andrew Tannenbaum. Okay, questions? Rao, go ahead.
Okay, sir, I have one more question. Are slides enough for the preparation of the exams or to get the concept, or do we need to read these books also?
Yeah,
if someone attends the class, okay, you continue.
Should be enough, but everyone learns in a different way. So maybe someone did not understand a concept that was presented in the lecture and wants to have additional literature on this exact topic. Then you go to the secondary literature and try to fill your knowledge gaps.
I understand.
To answer your question in short, slides should suffice.
Thank you.
So I had a question. Yeah, so you recommended the book for theoretical knowledge and the information that may be lacking in the slides, but can you recommend some videos or YouTube videos which have more practical demonstration of Linux or whatever we will be using, more practical stuff?
Difficult because the course is designed around these books. So this is the main source of information. So I won't recommend any YouTube videos because these may diverge in subjects that we discussed. In both Tannenbaum books, there is a part of exercises at the end of the chapter. So if you want to do practices, then please do the exercises at the end of the book.
Thank you.
where you can get these books. These are in our library, and the online library is called Opus. Let me just check this for you. Did I get it? Not Opus, OPAC. You can switch. This is not optimized well. You can switch to English here, and then so it's opac.th.dec.de, and if you put in Tannenbaum and search for them, you get all Tannenbaum books. So, for example, modern operating systems. And if you click on that, is this available as PDF? I don't know. I don't know if. Guess it's not available online. So if you are in Deckendorf, you can go to the library and you can borrow the book. If you are not in the library, well, you would have to buy the book then. Print save, no. There's like no online version of this. Additional copies available for computer networks? Oh, no. So they are in the library. Yeah, they are in the library. Okay. Question why the lecture is not recorded. What if someone cannot attend the lecture? So I have I guess some colleagues do recordings. I don't do recordings for the following reasons. I want you to attend to the lecture. So attending to a lecture is a commitment that you do. You need to, depending on the time zone that you are, you need to get up, you need to prepare for the lecture, and you need to work after the lecture. This is the way how we do, or this is the way how I do things. If I would record the lecture, then maybe 5 to 10 people will attend to the lecture, and all the others will just then either ignore the lectures or will consume the lecture offline at some other times. And for me, it's important. Well, my goal is for you to pass the module in the first attempt with a very good grade. So this is the baseline. And for you to have to attend to the lecture, to every week work on the module, and also work on the practice exercises, get the solution through the practice exercises, this contributes to that goal. And therefore, I do not do the recordings, I do all the lectures live to have like more interactions, because you ask questions, right? And this asking questions is very, very valuable to you. And interaction only works if we have a full classroom / Zoom room for us to get in a discussion. And this is the main reason why I don't do recordings. Okay, any further questions? Then let me switch to the next slide deck, which will be introduction. Slides. Oh boy. So my presenter crashed. Let me restart this real quick. You can still hear me, right? Yes, okay. So let me restart this real quick. Slides are so crashed again. What is this? Okay, trying again. There's something wrong with these slides. Hopefully not. Okay. Move this here. So it did not crash, which is good. Works. Okay. So next section would be introduction to operating systems, and the introduction is quite comprehensive because we start at the basics, right? So you do not need any prior knowledge on operating systems or networks. We always start from the basics, and the basics in operating systems are computers. So, well, everyone knows what a computer is, what a computer does. But to formally introduce the term and define the term, well, a computer is a digital electronic machine that we as humans programs to carry out tasks. And a task is like a sequence of operations. These operations can be arithmetic, so we can add two numbers, for example, or we can multiply two numbers, or logical operations. Logical operations like comparing two numbers. Are these two numbers equal? Or is this number greater than the other number? Logical operations will be a major subject in the Foundations of Computer Science course that you take this term. But, well, this is what a computer does. Calculations and logical operations. And this is how programs are composed of. This sequence of arithmetic and logical operations is what we call like an order that we give to the computer, and this is called also an instruction. So a program is composed of a sequence of instructions that the computer carries out one after the other. But the computer cannot understand every instruction. There is a special set of instructions that are possible. And this is what we call machine language. And machine language is 2 or 3 years ago, or 5 years ago, I would say, well, every computer, every laptop basically has the same machine language, but this is not the case anymore. Can someone, or does someone know why? I will tell you. It's Apple. Apple released the M1 or M2, the newer variants, MacBooks or machines that they sell. And these M1 Macs have an entirely different machine language than laptops, for example, that run on an Intel CPU or an AMD CPU. So these have two fundamentally different instruction sets, so they understand different machine languages. The same, I have my smartphone in my pocket here, so I have this smartphone here. This smartphone, basically, it's a computer, right? It has a CPU in it, it has everything in it. It's a digital electronic machine that can be programmed to carry out things. But this smartphone has an entirely different machine language than my notebook, for example, because they have different architectures. The one is based on ARM CPU, so this is how these are called, and the others are x86. This is like the architecture that Intel CPUs, AMD CPUs support. And these two architectures, ARM versus x86, this defines the machine language. And both like sets have benefits and drawbacks, but this is out of the scope for now. But the architecture, the CPU of your computer defines what machine language is supported. And this also means that you can run programs that are designed for this kind of architecture. So if I have a program that I can run on my AMD laptop. So I have an AMD laptop, for example. This program can execute on an Intel laptop, but this program cannot execute on an Apple ARM M2 laptop, for example. Yeah, and the sequence of instructions, this is called a computer program. Question, machine language, whereas we have different operating systems? No, the machine language does not depend on the operating system. The operating system also needs to support the machine language, but the machine language depends on the CPU that you have. If you have an Intel CPU, this defines the architecture of your computer and also defines the machine language that is supported. If you have a ARM-based architecture, then you need an ARM-based operating system. These two architectures need to fit together. Here on the slide, you see a more or less modern computer. So this is actually my computer. So I took a picture and I tried to highlight all the major components of a computer, because a computer is quite complex. So it is composed of different components, as you see here. So the main board is where every component is plugged into it. So it's on the back on this computer here. So this is my desktop computer. And the brains of a computer is the CPU. CPU is short for Central Processing Unit. And all the instructions that are carried out in a computer, this is done by the CPU. So this is like the unit that does all the calculations. And you see, you cannot see the computer directly here. So we put a cooler on top of the CPU because there are a lot of instructions and a lot of arithmetic and logical operations a CPU carries out in a second. So this is in the range of billions. So multiple billions of calculations per second. This is done in the CPU. This causes a lot of heat, and this heat needs to go somewhere. So we need large cooling components to get the heat of the CPU into the air. Then we have a graphics card. Oh, graphics cards are expensive. So if you like to game a little bit at the evening, I'm such a person. I like to play some video games at the end of the day. So you need a potent graphics card. Graphics cards are expensive. If you buy a newer NVIDIA graphics card from the 40, the most recent series, then you have a range from 500 to 2,000 euros. And if you're like in the mid-range, you need to at least pay, let's say, 800, 700 euros. So graphics cards are expensive, and graphics cards are responsible for putting something on your display. And if you are a gamer and you want to have a lot of frames per second in your game, you need a powerful graphics card, which you plug also in your computer. If you just do like browsing, YouTube, a little bit of Netflix, then you don't need a sophisticated graphics card, but you need a graphics card. So the graphics card is responsible for putting something on your display. Yeah, power supply is at the bottom here. This power supply, as the name says, supplies the power to all the components. And then on the right-hand side, things get a little bit more interesting. For our theoretical discussions, we have different kinds of storage. So in our computer, we do calculations and we handle information. And we do this in different layers of memory or storage. We have RAM, for example, which is the main memory. And this is a volatile memory. So if you turn off your computer, every information that you store in RAM, it's gone because it needs power. It needs power on. On the other hand, we have like the M.2 SSD here or a hard disk. These are secondary memories. So RAM is a primary memory. It's volatile. Secondary memory is non-volatile / persistent. So if you store any information on a file on an SSD disk, you don't need to power to persist it. The difference between these two, an M.2 SSD and a hard disk, is cost and capacity. So typically, these M.2 SSD disks are more expensive but faster, and a hard disk is less expensive but a little bit slower. Let's keep that in mind. A question, are these slides on iLearn? They are already on iLearn. You can download these slides. So this is what actually happens in reality in a computer. And now we switch the perspective a little bit to a more like architectural style. The main model, how a computer is made up, is called the von Neumann architecture, because von Neumann invented this architecture. And in this slide, this diagram shows on like a model-based diagram. So this is a model, and the model is not 100% accurate, but still illustrates how computers work. And we have like 3-4 main components in a von Neumann architecture. You see the main component here with blue background, which is the central processing unit, or the CPU. The CPU is composed of subcomponents. For example, we have a control unit in there. We have registers. We have the arithmetic logical unit inside the CPU. And then we have this kind of different types of memory. We have main memory or primary memory, which is called in the von Neumann architecture the memory unit. And then we have secondary memory, like M.2 SSDs or hard drives. And then we have input-output devices connected to the computer, like keyboard and mouse, which are input devices, or display and printer, which are output devices. A secondary memory is also an input-output device, because we input information, we can load information from files, and we can store information in files. And all these components together, these are connected via a bus. And now, the important information. So how does this von Neumann architecture work? Well, if we remember, we're talking about computers, right? And computers execute programs. A program is a sequence of instruction, like add these two numbers together, compare these two numbers, this and that. So arithmetic and logical operations is an instruction, and a program is composed of millions of instructions. And these instructions reside in main memory. This is the place where the instructions of a program need to be. If you double click on a program in your computer, well, the program is stored on the secondary disk, and through the bus system, the computer loads this program into main memory. And from there, the brains of our computer, the CPU, fetches the instructions from main memory and executes these instructions. So the control unit is the boss, so to say. The control unit controls and fetches these instructions from main memory, puts it into some storage inside the CPU. And these are the registers. So a register is another like memory. It's the memory that is directly inside the CPU, and it's not much. These registers, I mean, a modern CPU has 20 to 30 registers, and you cannot store a lot of information in these registers, just a small amount. In a 64-bit architecture, which are most of the architectures right now, you can store 64 bits inside a register. And then you have the arithmetic logical unit. I will abbreviate this as ALU. Then the ALU can then perform an arithmetic or logical operations on two values which are stored in two registers. So this ALU says, well, add register A to register B and store the result in register C. And these registers are directly next to the arithmetic logical unit, like in the circuit of the CPU, directly next to each other. the cache that you know, because there's a question in chat, like level 1 cache, level 2 cache, level 3 cache, it's still in the CPU. So this cache is located in the CPU, but not directly next to the arithmetic logical unit. It's a little bit far away and sits between the registers and the main memory. We will talk about cache memory when we talk about memory management, I guess in 2 weeks, 2-3 weeks roundabout. There we take a look, well, what is caching in the first place? What caches do we have in a CPU, and how does this work together? So we do not focus caches right now. Let's assume, well, we have registers, and the next level of memory that we have is the main memory. What is illustrated here is PC or AC. These are like the names of the register. PC is a program counter, AC is an accumulator. The accumulator register, for example, well, if you add 2 numbers in the ALU and you have a carry, for example, or you have an intermediate result, you can use the accumulator register to store this intermediate result, for example. And this happens pretty fast. So I have, so my CPU, admitting people, my CPU is an little i5 in the 13th generation. So it's an Intel CPU with, it boosts on 5.1 gigahertz, right? 5 gigahertz, meaning that, let me just calculate. So it's in the billions. It's in English/international, it's 5.1 trillion operations per second. So let's say 5 trillion operations, instructions per second in a modern CPU. This is crazy. This is crazy much. No human is able to do it this fast. Yeah, but I mean, to wrap up the von Neumann architecture, well, we have a CPU, and the instructions need to be fetched from main memory over the bus, right? So the bus, you can imagine, like if you drive on a German Autobahn or like on a road, information are the cars on the road, right? And you need to, this is information needs to travel from main memory over the bus to the CPU where it's stored in registers. When values for an operation is in a register, the ALU can perform the operation, like the control unit that controls everything. This like cycle is called the control unit here as well. Because, for example, I mean, if we have a calculation in the computer, we want to have the result displayed on a display, then the information travels over the bus. ALU, well, we talked about this, arithmetic logical units. Control units is like controls the operations, provides timing, control signals, and such. The CPU is the electronic circuit that executes the instructions, has registers. And here you have a table of like the example registers that we had on the slide here. So this is not relevant for the exam, so you don't need to know what a program counter is or a memory data register. You just need to know what is a register and what does a register make up. So register is very, very close to the CPU, like directly next to the ALU in the core of the CPU, and therefore it's super expensive, right? It's the faster registers get, the more expensive, or the faster memory gets. We can generalize this. The faster memory gets, the more expensive it is to implement. So registers are faster than RAM, but more expensive. RAM is faster than an M2.SSD, but more expensive. An M2.SSD is faster than a hard drive, but more expensive. Expensive meaning the cost of, let's say, a unit, like a cost of 1 megabyte to implement or to realize. Memory unit, well, it's when we talk about the memory unit in context of a von Neumann architecture, this means RAM. so main memory or primary memory. This is directly interfaced with the CPU, so the CPU can directly talk to memory, right? Quicker access than secondary memory, but not as fast as registers. We talked about this. And now, the next piece of important information, RAM is divided into locations. And every location has an address. And this address is an integer value. And we just start counting. So yeah, RAM is divided into memory locations, and each memory location can hold 1 byte of information. Quick excursus, if you do not know, because we start from the scratch. What is a byte? Right? A byte are 8 bits, and a bit is the smallest unit in a digital computer. It can take 2 values, a 0 and a 1. This is a bit. Why do computers use bits and 2 values? Because you can represent a bit in an electrical circuit pretty easy. You can think about like an electrical current. Is the current put on? Then we have a value of 1. So if we have like a voltage, a positive voltage, then we interpret this positive voltage as 1. If we do not have a voltage, 0 volt, for example, then we can interpret this as 0. And this 2 states, like voltage on, voltage off, you can represent this in a digital electrical circuit pretty easy, like switching the power on, switching the power off. And then you have 2 values, 0 and 1. This is, so zeros and ones are easy for the computer to realize technically and to work with. And this is the reason why computers use bits for all the calculations. A group of 8 bits is a byte. So this would be a byte. 0, 1, 0, 1, 1, 0, 1, 0. This is a byte. So 8 bits form a byte. Bit is either 0 or 1. Then the next bigger unit would be a word. A word is the amount of bits a register can hold. And this is based on the architecture. So nowadays we have 64-bit architectures. Before we had 32-bit architectures in the early 2000s and in the 90s. 16-bit architectures in the early 90s, and in the 80s we had 8-bit architectures. But now we have 64-bit architectures, and the impact of the bit architecture is, well, the width of the bus. So how many bit lanes does the bus have, which is aligned to the architecture, well, 64 bits, and also the amount of bits a register can hold. So in one register, you can have 64-bit, which is 8 bytes, because there's a factor 8 in between. And for data sizes, we use binary prefixes to denote the quantity. Well, it's a little bit different, a little bit difficult, because the SI, so the Standards Institute, they differentiate between the calculations on sizes and calculations on data rates, because sizes are denoted in binary prefixes, meaning we have a kilobyte, which is 2 to the power of 10 bytes, which is 1024 bytes. The difference between kilo and mega, so a megabyte is 1024 kilobytes, which is 2 to the power of 20 bytes. Gigabyte factor 1024, so 1 gigabyte is 1024 megabytes. 1 terabyte is 1024 gigabytes. 1 petabyte is 1024 terabytes. 1 exabyte is 1024 petabyte. So you know it, it's binary prefix, always to the power of 10 more. So 1 megabyte is 2 to the power of 20 bytes. 1 gigabyte is 2 to the power of 30 bytes. Binary prefixes. If we're talking data rates, and we will talk about data rates, or like anything that's not a size, then we have decimal prefixes. Then 1 megabyte per second, for example, will be 10 to the power of 3 kilobytes per second. So 10 to the power of 3 will be then the factor, which is a decimal prefix instead of a binary prefix. So be aware of that. In the exam, we will, for the sake of simplicity, always do decimal prefixes, because decimal prefixes are easier to calculate, and I don't care in an exam, well, if you do the unit conversion based on decimal prefixes. But if we are very technically exact, data sizes in binary prefixes, data rates in decimal prefixes. Okay, so 1 byte, 8 bits, 8 zeros and ones in one address. And we count the addresses with integers. We start at 0, and then we have 1, we have 2, we have 3, and so on and so forth. And if you have like 64 gigabytes of RAM in your computer, you have a lot of bytes in there and a lot of addresses. But these are like indexed or addressed using integer values. 65,535 is, I guess, is it 8 bits or is it 16 bits? I guess it's 2 to the power of 16. I guess I don't know. You can put this into the calculator. But talking about number systems, I don't know if you talked about number systems in an other lecture as well, but we can express numbers in different ways. What is very natural to us is this column here. It's the decimal number system. Decimal because we express numbers with 10 digits. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 digits. And we can express numbers using these 10 digits. So 40,000 in the decimal system is 40,000, right? But in math, we can do a change of the number of digits, which is the base. So for example, we can express numbers using 8 digits. Then we just use the digits 0, 1, 2, 3, 4, 5, 6, 7 and express the 40,000 only with 8 digits. And the respective number would then be, what this is 116,100 in the octal system. Octal system meaning that we only are allowed to use 8 digits. And then we can do this in binary as well, where we just have these 2 digits. I cannot say this number, but this number, what you see here in the first row, last column, this is the binary representation of 40,000 in decimal. Yeah, so the sequence of ones and zeros, this represents 40,000 in decimal. We can do this in hexadecimal or even in higher bases as well, where we say, well, we have more than 10 digits. We have 16 digits in the hexadecimal system, where we add digits, and as we do not have like digits anymore, we take the alphabet, right? So our digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Technically, we can do this. And 40,000 in the decimal system would be represented in the hexadecimal system as 9C40. Why do we do that? Well, I said before, computers can perform operations based on binary numbers, like current on, current off, voltage on, voltage off. So it's easy for a computer to represent ones and zeros in a digital circuit. So it's simple for the computer to do all the calculations in binary. But you see it in the column here. The less digits you have, the more digits you need to represent higher values, higher numbers. So in decimal, we need 5 digits to express 40,000. In octal, we need 6 digits to express the same value. And how many do we have in binary? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 digits to express 40,000 in binary. And the more or the higher the base is, the smaller the number in terms of number of digits. Yes. So in hexadecimal, we need 4 digits in order to express the 40,000. So programmers prefer hexadecimal numbers because it gets more compact. But still, it's just counting. We know how counting works. And if you encounter a number such as 9C40, don't be like hesitant or don't be afraid of these hexadecimal numbers, because these are just simple numbers. We can add them together, we can multiply them together, we can subtract these numbers. The reason why I'm telling you this is because these numbers for addresses in computers are typically expressed as hexadecimal numbers because they are more compact. But still, it's just integer values, right? How to convert a decimal number to an octal number, this will be part of the module Foundations of Computer Science. We will not cover this today in this course. And also, good information, whenever a slide is titled Excursus, meaning that this is just for your information, this is not exam relevant. So number systems will not be in the exam, excluded. So back to our von Neumann architecture. Well, how do programs execute on a von Neumann architecture? This is defined by the machine instruction cycle. I mean, we talked about it before as well. We have 4 basic stages which define the process by which a computer executes instructions. So the first stage is the fetch stage, where the next instruction is fetched from the memory unit. Then this instruction is somewhere in a register in the CPU. Then it needs to be decoded. The control unit then takes a look what bits and bytes are in this instruction. And depending on which instruction it is, it passes it to the ALU. For example, the ALU needs to perform like a comparison or an addition, for example, right? So the control unit interprets the instruction and passes it to the ALU, and then the ALU executes that instruction, so performs the actual operation, and then the result is stored in main memory again, or sent to an output device. So we fetch, decode, execute, store in a loop all the time until we terminate the program. These are the 4 basic stages which are implemented in any CPU. Well, I said it before, these CPUs are insanely complex, and we would need multiple lectures, multiple semesters to deeply understand how CPUs work in detail. Typically, a modern CPU has more stages because these stages are super highly optimized. And typically, a modern CPU has around 15 to 20 stages, which are executed then in parallel. And there are optimizations such as out-of-order execution and branch prediction and all these kind of things. But like in context of the model of the von Neumann architecture, this is what the machine instruction cycle looks like in a von Neumann architecture. These are the 4. In order to get a little bit more like a feeling on how complex it really is, I have some example instructions here in the slide. Again, you do not need to memorize these example instructions. These are just for demonstration purposes, but to explain again what happens in a computer, right? So the program is a set of instructions. Every row that you see here, every line, this is an instruction. Move AX, OXFFEC. This is an instruction, and this instruction lies at the memory address OX4000. So this, what you see on the left-hand side, these are the addresses in main memory where these instructions reside. For the sake of simplicity, we assume, well, we need 3 bytes space in memory to hold a instruction. So the first instruction is at address 4000. The next instruction is at address 4003, because remember, every address has 1 byte, or every memory location has 1 byte of like storage. If we need 3 bytes, well, then one instruction spans over 3 memory locations. So next location, next memory instruction is 4006, 4009, because we are in hexadecimal. So this is the hexadecimal notation, which starts with a 0x. 0x 4000C is the hexadecimal number of this instruction, right? And well, this is a move instruction, so loads the value at address FFEC into the AX register. This loads the value at address ATFF into the BX register. Then this instruction adds 2 to the AX register. This instruction compares AX with BX, and depending on the outcome, we have an operation which is JL. JL means jump if less. So if AX, or the value of the AX register, is less than the value of the BX register, we jump to the instruction that is given by this operand here. So we jump to the register 4006, which is line 3 here, and then the next instruction that is executed, well, is then this add AX2 register, and so on and so forth. What you see here is both. So you see both data and instructions. So instructions are in memory, right? So these instructions are located in some memory address, but also like values or data, like values for operands. Here, we compare the value of AX and BX register, and these depend on, here we have it in the first two. Here we load the value at this address into the AX register, and we load ATFF to the BX register. So at address ATFF, we have a value of 8. At the address FFEC, we have a value of 3. So we store in the AX register the value of 3, and in BX, we have a value of 8. Then we add 2 to the AX register, so AX is now 5. And then we say, well, is AX, which is 5, less than BX, which is 8? The answer is true, so we jump to this instruction and start executing again. And this is how computers internally work. To make matters worse, it's done in parallel. So we employ a concept that's called pipeline processing here. Pipeline processing means that all these steps, like fetch, decode, execute, store, all these are executed in parallel. So if you take a look at this diagram here, we have on the x-axis the timeline, on the y-axis we have the instructions. So in the first, let's say, time unit between t0 and t index 1, we fetch the first instruction. In the next time slot, we decode the first instruction and in parallel fetch the next one. In the next time slot, we execute the first, we decode the second, and we fetch the third instruction. And then in the next time unit, like between t index 3 and t index 4, we store the result from the first instruction, execute the second instruction, decode the third instruction, and fetch the fourth instruction, and so on. So we do this in pipeline processing manner, meaning multiple instructions are overlapped such that the CPU's ALU is always under full load. So, and in every in every time unit, the CPU should execute at least one instruction. How are these time units defined? So what makes up the time t0 and t1? Well, this is based on the execution speed of the CPU. So maybe, you know, if you bought a CPU already, one of the key performance indicators of a CPU is its clock speed, like 5 gigahertz or 3 gigahertz and such. And this is what this denotes is a clock signal, right? And this clock signal looks like this. It's a electrical signal where you apply a voltage here on the y-axis, YCC. In CPUs, this is a small voltage, 1.3 volts, roundabout. And whenever there is a transition from voltage high to voltage low, this is the time. So here exactly, this is like a clock tick, meaning that a next time unit is starting. Whenever there's a transition from high to low, we have it here at T1, we have it at T2, we have it at T3, we have it at T4, and so on and so forth. So this clock signal, like the transition from high to low, this defines how long such a time unit is. And you clearly see the faster the clock signal, the smaller these time units are, and the faster the CPU can operate. Again, CPU, insanely complex. Modern CPUs are not, I mean, a higher clock signal still makes the single core CPU better. But modern CPUs, I mean, they rise in clock frequency, but not as much as in the beginnings of the 2000s, for example. But I mean, they are so highly optimized such that the speed of the clock signal is still relevant, but not as relevant as it was like 20 years ago. Keep that in mind. But in general, well, the higher the clock signal, the higher the frequency of the clock signal, the smaller these time units get, and the more instructions you can execute. Modern CPUs execute, by the way, more than one instructions at the same time. I guess one CPU core has about 10 to 15 ALUs, so 10 to 15 execute steps at the same time, and it depends on the sequence of the instructions how fast the CPU really is. And again, this is something very, 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 very super complex. So there's a question in chat. What does JL stands for? It stands for jump if less. So this compare instruction, right? So this compares the values AX and BX. And depending on the outcome, so the result of this instruction is stored somewhere, stored somewhere in the register, like in the accumulator register. And the jump if less instruction takes a look into this register and says, well, the comparison that I did before, was this true or false? So is AX in fact smaller than BX? If yes, it performs the jump to this address. If not, it does not perform the jump, and execution continues with line 6 in this case. So this is some kind of branching. I don't know if you had your first programming lecture yet, and I guess if then else branches are not covered there yet, but still this is some kind of control flow. So you can jump to different addresses and resume the execution of the program there. Okay. Can you explain the VCC graph again? Yes. So what this is, it's the clock signal. It's an electrical signal, and this signal is shaped in this square form. This is how this clock signal looks like. Clock signal meaning it's an electrical signal which is high if there is a voltage VCC applied to. So VCC is the voltage of the clock signal, and it has it depends on the CPU how high this voltage is, but it is around 1.3 volts, roundabout. And if the voltage is applied, the signal is high. If no voltage is applied, the signal is low. And over time, you get this square signal, right? And this square signal, this defines the time unit a CPU, or more precise, an ALU or a control unit has to perform an operation. Because when the signal transitions from high to low, a time unit ends and the next one starts. So the control unit needs to finish the fetch operation in one clock cycle, or the ALU needs to finish the execute operation in one clock cycle. And one clock cycle is defined by a transition from high to low in the signal. Exactly. It's like alternate current. Current on, current off, current on, current off, current on, current off. And transitioning from on to off is like a border for a time signal. And all other components need to work with this kind of clock signal. Okay. So What we do next is the first task. So let's switch over to Ilan. There's a task computer architecture. There are 3 parts where we do the first part in class, and all the other parts are designed for you to do as homework. This works as follows. Well, I give you time in order to accomplish part 1 of the task, and then we discuss the outcome of the task. I will present you, or will present the solution, and we will have a discussion if there are any open questions. All the other parts that are declared as homework, I will talk about these at the beginning of the next lecture. So we have like an entry point for the next lecture. This will always be the first part of a beginning lecture talking about the outcomes of a homework. So access speed of RAM and the von Neumann bottleneck, this is an assignment to you. Please do this at home for the next time. And we will discuss the solutions at the beginning of the next lecture. What we do now is the following. Yeah, what we do now is we make a break because it's, oh no, break is at 11:30 because break is right now because we started at 9:45, 90 minutes are over, so break is right now. So what we do now is make a 15-minute break where you can refresh your brain. And after the break, we will talk about the access speed of registers, and then we work on this task. So let's have 15 minutes and talk to each other in 15 minutes. It says task assignment, but let's do a 15-minute break. Let's talk again in 15 minutes.